Now, when we chopped up domains using discrete cosine or sine transform, or FFTs, we took a domain and we chopped it up evenly, right? So now we're going to start looking at this and chopping things up. But since we want to use the cosine transform, what are we chopping up here? We're actually going to start chopping up x, but really, since we're doing the computation with the theta variable, we're chopping up theta evenly. Now, if you chop up theta evenly, it's different than chopping up x evenly. I'll draw a picture here. I want to chop up the theta variable evenly. Here's how I do it. M equals 1, 2, all the way up to n. So let me draw a picture here. Here's x, 1, minus 1. And this is x cosine theta, so it's like being on an arc around this thing. You're on a circle, essentially, right? With theta being this angle. And what you're going to do is going to chop up the arc evenly. Right? Chopping up the theta variable. So I'm going to just chop up points here evenly, all the way around this arc. Evenly spaced. That's simple d theta. By the way, what does that imply for our dx's? I no longer am working on a uniformly chopped up domain. So what are my x variables? I'll just do that half. Notice what happens. My dx in here, much bigger than my dx over here. And in fact, I have a clustering of points on the boundary. So when you work with the Chebychev polynomial, you're automatically going to have this clustering of points on the boundary. Now, here's the good news and the bad news all together. The good news is the following. Suppose you have a problem where the boundaries are playing an important role in the dynamics. In other words, stuff is happening at the boundary. You automatically get more resolution on the boundary with Chebychev. Here's the bad news. Suppose nothing's really going on in the boundary, everything's happening in the middle. Then that means you have to increase your resolution a lot in the middle, which means you're having a ton of points on the edges. You see the problem? So that's the bad news, potentially. It's only potential bad news. It's only potential good news. It all depends upon the problem you're actually working with. But remember, the extra piece of good news is you're doing this in n log n. Right? So you can't lose. I mean, you can, but I always like to say n log n is like it's a winner's choice to take. Okay. All right. So this is critical, and we're going to see this in practice. So we'll pull up a Chebychev code. We'll do it in class. We'll use this idea here, and you'll see what happens to the boundary. And in your homework 5 that I gave you, right? Yeah, homework 5 has you working with this Chebychev polynomial. And then you're going to, I have this statement in there. Be sure to rescale and make sure that you do things right, because a lot of times people forget that they're working on when you go plotting, you can't plot on an evenly spaced domain. You have to plot. Remember that you're doing clumping. Okay? So that's something we have to think about. Okay, so these are just kind of facts about the problem I'm throwing out today, sort of get you familiar with Chebychev, right? So now Chebychev has this connection. It's fast. It's a FFT-based routine, really, in the end, because of the connection to the cosine transform. So you not only get spectral accuracy, you get n log n speed. Okay? But cost of it, you're working now on a domain that is not uniform, not uniformly spaced. There it is. Okay? So you pay that price. What? Yeah. Yeah.
So this formula for the x sub n, does that include the endpoints, that cosine thing? Do they
yes, this goes all the way to 2 pi. Here, so unlike unlike when you do the fast Fourier transform and you throw out the last point because it's the same as the first, that's no longer true in the DCT or DST. So the discrete sine and cosine transform no longer have that point the same as the first. It's actually you have to go to that last boundary point.
And the x is inside the bracket cosine, right? It's one
Yes.
times x takes
Yeah.
cosine of all that.
Mm-hmm.
You take the cosine to that as well. Is that whole schmear in
Yeah. So all this is bracket there. Yeah. Okay. Couple last observations, most relevant to us, which is what I'm really interested in is what happens if I take some operator and operate on f. In particular, what I'm really interested in is how do derivatives change, or what happens to derivatives under this Chebychev idea. Why am I interested in this? By the way, we were very interested in this in the context of Fourier. In particular, we had this beautiful result. And you're never going to get a result this nice ever in your life again, by the way. Things just don't work that nicely all the time. Right? Here is how derivatives relate. This is, awesome. That thing's great. And it's so simple and it's nice, and that's the only place where it's that simple and that nice. Okay? But we want the same kind of thing here, which is what I want to do is I have a differential equation or a PDE, and I want to say I got to take derivatives using this Chebychev polynomial. I have an expansion of this function f of x, right? Which looks like this. The question is, what happens and how do I compute, for instance, a derivative? Okay. So, in fact, what I really want to know is the following. If I operate on this function f with some operator, I can think about it again. It's another expansion in terms of the Chebychev polynomials. And the question then really is, what is the relationship between the b of n and the a of n? Okay? In the Fourier transform, the connection was just you put an ik in front. That's how they connected. Here, it's going to be more complicated. But still, you can compute these things. So let me tell you the most important one. Suppose that L is a derivative. So in other words, what this is going to compute here is f prime. So this is going to give us f prime. And if we do that, then what we have is the following formula. So you take your a's, some coefficients p, here, which is p, you sum up, and your coefficients a, put a factor of 2 in front, and you sum up over these things. And I have here that, for instance, let me get this right. C0 is 2, otherwise C of n is 1. And then the b of n, and that's how you get the b of n. So you have this relationship between the b of n and the a's. So if I want to get b2, b2 will come in here, and I'll have to do the sum to get out over all the a's with some coefficient factor, and I'll get these b of n's. They're the formulas, and you can implement them on the computer. That's the important thing. I have some other formulas there. And by the way, I'm not even sure if that's right. How do you like that? And I don't care. Here's why. Because we're going to write a code. We're going to just develop it in class. And the point is, what I'm trying to illustrate, and maybe not even that effectively, is that when you have your a of n's, there is a connection between the a of n's to the b of n's when you operate on this thing. So it's like a matrix operation to tell you, how do I get now the derivatives? Well, if I have this function and I have the a of k's, it tells me how I can get the b of n's to value the derivative. And I'm going to basically generate a matrix that does this for you. Okay? So that's the big deal with this picture here. So you see this? That's not as pretty as that. Okay? Unless you have a warped sense of prettiness. But that is just, that's that. Okay? Just not in a very elegant way, but that's the way it works out. Okay? So Chebychev, so all you have to keep in mind is this. There are two spectral algorithms, only two, that give you n log n speed. The FFT and Chebychev. Why would you use Chebychev? Right? So why would we use FFT? Why would we use Chebychev? Chebychev, or FFT, works in three cases. Periodic domain, pin domain, no flux. Chebychev actually has a little bit higher level of, we can play around with the boundaries, by the way. We'll talk about it later. But Chebychev allows you a little bit more flexibility in what you can do with the boundaries. And that's why you might use it. It's for a finite box, and you can get a little bit more flexibility in boundary conditions. The one thing I want to point out is the following. Okay, so I'm going to make this analogy later about picking techniques. What your objective is to pick the fastest, most accurate technique possible. And there is an Achilles heel to using spectral methods. The Achilles heel is the boundary conditions. When you use these special functions to do the spectral transform, you have limited yourself to a very small boundary condition set. And this is where it kills you. So anything that will expand your offerings in terms of boundary conditions is always a win. And this is why we talk about Chebychev, for no other reason. Okay? So we'll go into detail more about that later.